Howdy. I was asked to do a video on logistic regression, and when we did the whole gradient descent series back a few weeks ago, maybe a month ago, I used logistic regression as just an example of a more complicated model. We were using our minimization code to find optimal parameters for. And what we did was actually considerably more complicated than the simple linear regression that we did right before that, in that not only is it a more complicated model, it's a classification model and there's exponentials and whatever involved, but I did the case where there are more than one or two free parameters. I think we did like a two parameter system. To kind of equate it to linear regression, it would be as if we were fitting a plane to a series of a bunch of three-dimensional data, as opposed to fitting a line through two-dimensional data. So I wanted to go over all the bookkeeping that's involved in doing that. So what I'm going to do is go back to linear regression and show how to fully vectorize that code, which we did not do entirely in that original video. And then I'm going to extend that linear regression to fitting a plane or hyperplane to data. So you'll see that the bookkeeping is, while annoying, does give us a lot of flexibility and enables us to handle a wide range of problems with basically the same code base. I wanted to do this before we actually dive into logistic regression, and that video will probably be still a few weeks out. I'm swamped with other projects, but I did want to get this out there first. So let's just jump into it. So NumPy has a series of quirks that I find somewhat annoying. As an example, let's create a matrix, an identity matrix called, I will call it I. It will make a 3 by 3 identity matrix. So there we go. If we wanted to multiply it times another matrix, so A is equal to, I don't know, let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, and close that. Need a close parenthesis, and this needs a np.array. Okay, I think it is fixed. Let me just print it out so we can see it. Okay, there are two matrices. Now I like to be very specific in the way I define these arrays and the functions I use to operate on them with. For example, I times A in MATLAB makes perfect sense, but what do you think it does here? Well, it happens to be, I believe, element-wise multiplications. You multiply each element in one array by the corresponding element in another, and you get this. And you can see, since most of these entries are 0, it zeroes out the entries of this product array. If you wanted matrix multiplication, so the identity matrix times A should just give you back A, you would have to use either, they have an operator at, which does matrix multiplication. So this, obviously the identity times that just gives us back our array. But I like to be very specific and use matrix multiplication, which is in NumPy it is matrix MATMUL. So I'm going to be using that for matrix multiplication. And for element-wise multiplication, rather than just the time symbol, I'm going to use the np multiply command. So that does the element-wise multiplication. Now for matrices that are kind of obviously shaped like these 3 by 3 matrices, this is not that important, but things get a little quirky when you deal with matrices of other shapes. So to get around these quirks, what I'm going to do is basically, as I said, all these operations are going to be done explicitly, and things like parameter vectors. If I had a parameter A, which is a vector, let's say it's np.array, and it's 1, 2, 3, print A. What's going on? How strange. But anyways, I'm going to take this array A and I'm going to reshape it to be, in this case, a column vector, and explicitly say 3 by 1. Likewise, sometimes you get situations like if I have an array, let's go np.ones. Let's make this 4 rows and 2 columns. So when you grab like a specific column, if I grab this column, the second column here, and say b is equal to a1 print b, you see that this is essentially now not a, it's a one-dimensional vector. It's not a column vector or a row vector. So I would also reshape that. So if you want a video specifically on the kind of the quirks of the way these vectors are ordered and how they compare to MATLAB and the differences between the two, let me know. But I just wanted to get this out of the way at first. Okay, so I deleted all of that. And now a bit of notation. When I did linear regression in the past, I used this equation here, y is equal to mx plus b for our line. And I'm going to replace this to make our notation consistent with the logistic regression, which we're going to do in another week or two. And I'm going to write the equation of the line as y is equal to theta 0 plus theta 1 times x. So I'm just replacing b with theta 0 and m with theta 1. And that's just going to lead us to our multi-dimensional case down here. So if we have more than one independent variable, we can write, oops, typo here. We would have y is equal to theta 0, theta 1, x1, theta 2, x2, and so on. So for our one variable case, we had in past used data generated like this. We created some random numbers, kind of put some scatter into the y dimension, y direction, and then used the polyfit function to get the slope and intercept. NP, oh yeah, the browser. I had accidentally shut down the browser, so I need to rerun everything. Okay, so that was the graph. This is the slope and intercept. So let's redo this basically in a fully vectorized way, taking advantage of this notation. So in, again, the previous videos we did on this, for gradient descent, we wrote the gradient like this. We had a function that calculated two separate values, the derivative with respect to m and the derivative with respect to b, and these are equal to these expressions here, and then we just combine those into a NumPy array and return those. Okay, so I replaced the m with theta 1 and the b with theta 0, and now I want to come down here and define a couple of vectors, and I just want to concentrate on this theta 1 x1 plus theta 0 term here. So I'm going to do my parameterization like this. I'm going to define a vector capital theta. Again, it's a column vector like we said we're doing, and that is going to be equal to theta 0 and theta 1. Likewise, we're going to create another vector capital X, and it's going to be built like this. So we're actually going to create kind of like a dummy variable 1, and underneath that is going to be x, or x sub I in this case. So we ask ourselves then, what is this dot product of theta and x? Well, we can figure that out just by taking the transpose of theta and multiplying it by x. So let me write that out explicitly. So theta transpose x is equal to, theta dot x is equal to theta transpose x, and we can write that in matrix form here. So we have the row vector of our thetas, theta 0, theta 1, times this column vector 1, x sub I. So what is this matrix product equal to? So obviously it is just this. It's theta 0 times 1 plus theta 1 times x1. So we get back the equation of our line. And now our x values that we have here, because we're going to need multiple x's because we're summing over all the entries in the array. So our x matrix up here is not really a matrix, it's just a one-dimensional array. Print x. Okay, here it is. And we want it to be a column vector as per our discussion on notation. So what I'm going to do is come down here and say x is equal to, actually x dot shape is equal to x dot size, comma 1. So here's our vector, but we want a bunch of 1s as kind of a dummy variable before that. So let us alter this a little bit, And we'll create a vector of ones the same size as our lowercase x here. So let's go, let's just call it ones is equal to np.ones, and it's equal to x.shape is the shape that we want that matrix. Let's just print it out. Let's get rid of this print x statement, and just to debug we will go print ones. Cool. And just so we have access to our original x's and ones, I'm going to create a separate variable I'll call, I don't know, I'll call it capital X. And that'll just be equal to np.hstack for a horizontal stack, ones, comma, x. And let's just print that out to make sure we're getting the correct values. Excellent. So one thing to notice here, if we pick out a random row vector, let's pick out this one here, it's not in the same format as we used down here where we had a column vector, obviously row vector. So when we make use of this, we will generally have to take its transpose. So I'm just going to print out the transpose. There we go. So we get this, this particular 1, 1, 4 or 1, 3 vector are now in column form, so we can make use of that. So let me just get rid of this. And now I want to come down here and I want to basically talk about what would happen if we took our theta vector and we use that capital X transpose here instead of this lowercase x. So I just wanted to type out some things in general, so I'm going to make this a markdown cell. So consider a matrix equation like this, where you have a vector that would correspond roughly to our theta vector, and I'm going to denote it as a u here, multiplied by some other matrix. In this case, it's 2 rows by 4 columns. Well, I'm going to call, for the sake of convenience, this first column of this matrix, I'll call it V1, second column V2, and so on. So if you actually work this out, what does this kind of compute to? Well, this is equal to this u vector dotted into V1 is the first element in a new product array. Then it's u times V2 is the next element, u times V3 is the next element. So what we end up with is a row vector whose elements are the dot products of our vector u with the corresponding columns. So if we were to have our, let's say our u was our theta transpose here, and our this rectangular matrix here were essentially the matrix we built up here of all of ones and x's. This would be what? This would be the dot product of each term, which we said was basically this here. So then if we take that, we can subtract off y, multiply it element-wise times our x elements, and that is our summation. In other words, we get a row vector of, from our dot product, our subtraction gives another row vector, and we multiply it element-wise, we get back our row vector, and then we just use a summation, numpy summation command on that vector. And we also get rid of this equation here. Since the first element of our x array is 1, so this will become a 1 for that element, so that just becomes 1 times 2 is 2. So that just gives us back this. So we get rid of this equation altogether. And then as we go up to higher indices, higher values of I, if I is the next element, that becomes that actual x value. Yeah, so having done all that, we can actually build our code now. So the only thing I'm going to do up here is make sure our y matrix here is a column vector. So I'm going to come down and say, I don't know, I'll put it here. Y is equal to y.shape is equal to y.size, comma 1, and that should do it. So I'm just going to come down here and paste in our gradient descent code from the video on gradient descent. Let's just make sure that runs. It does. Excellent. Let's move on. So I've also copied the functions for the cost function and gradient from the last video on this. These are just for reference points. I'm just going to rename them, maybe cost function old and cost gradient old. They're just here just so that we can look at them if we need to. Let's see, underscore old. Okay, so let's just make sure our x's and y's look good. So print capital X. That's what we want. And what are the y values? Those look good too. So let us now define our new function. Let's call it just linear regression cost function. So linear regression cost function, and we don't really need the cost function for this. It was just for debugging purposes and visualizing the convergence in the gradient descent function. So we want to take our x0, which is our guess of the parameter vectors. Let's call that theta, just to be consistent with what we did before. So theta, x, and y. And as I mentioned above, to get the x's in kind of a column form, we need to take that x transpose. I'm just going to do x equals x transpose there. And basically all we have to do is return the cost function. So let's call that j, and that's going to be equal to, I'm going to build this in a little bit of a piecemeal way here. It's going to be equal to some quantity, and it's going to be y transpose, because we want y as a row vector, because from up here we said we're going to get back a row vector from this dot product here. So let's see, where was I? Y transpose minus np dot matrix multiply matrix multiplication of theta transpose and x, and we need to square all of this because it's the sum of the squares. So I'm going to come over here, np dot square, and then we need to take the summation of this resulting row vector. So np dot sum, that should do it, and I just need to return it, of course. Return j. So let's just test this out. Let us create a dummy value of theta. Let's just do a 1, comma 1. So np dot array 1, comma 1 theta dot shape, just to make it a column vector, is equal to 2, comma 1. So print linear regression cost function. Let's test it with the old. So theta, x, y. And let's just do the same thing here. Let's just copy this, paste it without the old, so our new function. And of course there's the problem, and it's in the matrix multiplication, and it seems to be a size issue. So let's just go back into that function and print x.shape, print theta.shape. So that's right. That is not right. Why is x a row vector? Print x. Oh, because I have to pass in the capital X here. That's what I did wrong. So yeah, 138.52, 138.52. These two things are identical, so that looks pretty good. Let us go and remove this kind of debugging code here. And let's move on to the actual gradient. So I'll keep this for now. So let's put it in the same cell as the cost function. We're going to define gradient descent. We call it what? Linear regression gradient. Linear regression gradient. It took our theta parameter, and it took our arguments passed in as a tuple. So those would be the x and y values. So, and the way we structured it previously was our x values were the first argument of that tuple, and our y values were the second argument. And just as before, we're going to do x is equal to x dot t for transpose. And so our gradient is, where is our gradient? So we're going to need that same y, the same transpose term, or dot product term we had down here. Where are my functions? So we're going to need this term here. So let us come down here and say, I don't know, gradient is equal to y transpose minus np dot matrix multiply theta transpose x, close that, and then we need to do a element-wise matrix product of this with our x values. And I'm not sure actually, because our x values are two-dimensional. This is, I believe, a one-dimensional vector. Let's actually do this before we do anything else. Print gradient dot shape, return gradient. Actually, we don't need the return at this point. And let's come down here and do gradient is equal to np dot multiply minus 2 times x gradient, print gradient dot shape. So let's come down here. Let's comment these out and just call these functions and see what the shapes of these various things are. This, I believe, is a one-dimensional gradient. Where's my mouse? This is, I believe, a one-dimensional row vector, and this, I believe, is a two-dimensional. It's a square. It's a rectangular matrix of same number of columns as this, but only one row. And I wanted to see if it broadcasts these together correctly. So I just want to see what the shapes of these are. So I'm going to come down here and I'm going to say my args are equal to capital X and lowercase y, and I'm just going to call that function linear regression gradient descent. And I believe we didn't have the word descent in that original function, so maybe I'll take it out in a second. But anyways, theta and args, that should do it. How the hell did that happen? Yeah, it looks like it's broadcasting them together. Let us just do it explicitly to avoid any ambiguities, so that NumPy is not making assumptions about what we want. So let's just kind of look at these 3 point something, 40 something down here. So this code, what I believe it is doing is, let's do this. Gradient is equal to numpy.vstack. And we want to stack gradient and gradient. Three something, 40 something. So yeah, that's what's going on there. I think this is a little bit more clear as to what's going on, so it's a little more explicit. So that's what we will do here. So let's get rid of the print statements. Let's get rid of the print statements. And I believe we called this old function just gradient. So let's just get rid of this word descent here. And let's get rid of it down here before I forget. Okay. And now let us actually, first we have to do the summation. So the gradient is the summation. It's a two-dimensional vector. It's the summation of all of these columns for each row. So sum of all these and then the second element is the sum of all these. So let's come up here and just say gradient is equal to np dot sum. We're going to sum the gradient, and we're going to sum over the column. So axis is equal to 1. And let's test it by calling our original code. So we have some numbers here to play against. So let's just wrap this in a print statement. Let's copy this. We'll just copy this. We'll come up here and paste it in. And our args are slightly different because we needed the capital X for the fully vectorized code, and this just needs the lowercase x, so it's going to be x comma y. So looks good. And okay, so the numerical values are flipped around because when we built this theta vector all the way up here, where did we first define it? The first element of that array was the intercept term, and the next element was the slope. And then when we defined our original run, where do we define it? Down here. We returned it in the opposite order. So this was the slope, this was the intercept. So that's why that's different. It's not going to make a difference in our code. So again, I'm just going to comment those out, and we're going to actually solve the problem. So I'm going to keep those args actually, and come down here. Where's our gradient? I actually want to make this a column vector. Make sure it's a column vector. So grad dot shape is equal to grad dot size comma 1. Run that. Run that. And now, in principle, all we need to do is call our function. So theta counts is equal to gradient descent. I believe we took our function, which is linear regression gradient descent, linear regression gradient, I'm sorry, and our initial value of theta. Seems to run. Let's just print out the results. So an intercept of about 0.3 and a slope of 1.9, which I believe is the exact same thing we had up here. Yeah, 1.9 and 0.3, 0.314. Outstanding. Okay, so that was a simple one variable case, and now you're going to see how simple it is to extend this to a 2 or 3 or 4 dimensional case. We're just going to do a plane, but you'll see that it's essentially exactly what we did before, and we can just repurpose all of that code that we just wrote. And you could even extend this to do things like polynomial fits, where instead of just linear relationships, you have like quadratic, cubic, quartic, that type of thing. It's the same exact thing. You just replace your other variables with, the square, the cube, the fourth power, or whatever you're doing. I don't think I'm going to do that in this video, as we're getting a little long. Now it's probably going to be well over half an hour. So let's just get to this and get going. So I'm just going to generate data for a plane. I'm just going to pick a bunch of random x points and y points, and I'm not going to bother to add any random noise to the z direction. So this is the equation of our plane. So the x coefficient is going to be a half, the y coefficient is going to be minus 3/4, and the term that would correspond to the intercept will be minus 2. So let's run that, and let's actually plot that and see what it looks like. So up in the imports, I've already imported the 3D plot, so let's just plot it here now. Okay, I had to look up how to actually do the plot. This is what it looks like, and you can kind of see it's a plane. Unfortunately, in Jupyter, you can't really rotate this around without doing a lot of other work. I usually use MATLAB for my 3D plots, or even 2D plots. So it's a plane. We should be able to reproduce this easily enough just by basically just using the same code we had up here. All we need to do is create our theta vector and pack our x and y and z vectors correctly. So let's come down here and just knock this out. So I'm going to concatenate, make our capital X vector by kind of joining together the x and the y's. the shapes should be all correct up here. Yeah, they should be all good. So let's define our theta. np.array. We're just going to guess an initial values of all ones. And then we need to make sure that this is theta.shape is equal to 3 comma 1. And let's just come down here and print theta to be sure. Invalid syntax, need an equal sign. Misspelled array. Misspelled theta, Jesus. Okay, so that looks okay. So I'm going to just get rid of this print statement. And now we should just be able to call our gradient descent function. So theta and count is equal to gradient descent. Our function is still that linear regression gradient. Our initial value is theta, so that should run. Oh, I know, I forgot to pass in my args. I'm just going to write it explicitly within the function call. So that's our capital X and our Z values. Matrix, oh, I know, I need to also, where do I define my X's? Right here. So what I need to do is pad these with ones. So ones is equal to np.ones. Let's make it, the size will be x.size, comma 1. Make sure that actually runs. Okay, so the error is still in the gradient function, so I should be able to come in here and write ones. Okay, so that problem was just that I had overwritten a variable somewhere in a different cell. So it's fixed, and now the issue seems to be that we hard-coded, where was it? Up here. Where we stacked the vector here. So, I'm sorry, right here. We originally stacked this vector 2 times. So what I'm going to do is get rid of it and just see if this runs as it is. I'm just going to rerun the whole sheet and just to make sure I'm not overwriting values. Okay, so I'm sorry about that. I don't know what happened, but I needed to define this explicitly outside of the function call for some reason. Otherwise, it was still picking up the old arguments, but with the new theta. So all of the dimensions, matrix dimensions, did not work out. So let's print these and see how good we did. So print theta. minus 5, 2.5 minus 0.75. Perfect. So yeah, that is what I wanted to go over in this video. Basically, just rewriting everything in a purely vectorized way where we could use the same gradient function to find multi-dimensional fits as well as one-dimensional linear regressions. So hopefully this going over this bookkeeping in detail will help when we go on to logistic regressions. Okay, so that's about it. I will just clean up this notebook. I will upload it to GitHub. I'm not going to do any polynomial fits now because this has already gone on way too long. But I just wanted to go over all the bookkeeping and stuff that's involved with this so that when we move on to logistic regression, it's not just coming out of thin air like it did in the original gradient descent series. So if you have any questions, feel free to leave them in the comments. And until next time, I will see you.